Algebra 3, Chapter 3, Section 4, Zeros of Polynomial Functions. The fundamental theorem of algebra basically says that a polynomial will have as many zeros as its highest power. This theorem is an existence theorem because it tells you that the zeros are out there, but it doesn't really tell you how to find them. If you think back on the graphing we've done so far, you may doubt this. I mean, we'll graph something with, a degree of 5 and it only has 3 x-intercepts. Or maybe even none. Well, degree of 5 would have to have at least 1. But, you don't see all of these intercepts that it supposedly has. Well, let's explore the reason for that. Look at the graph of x squared minus 6x plus 9. There it is. You will notice that there's only one intercept, but there should be 2 according to the fundamental theorem. In this case, when we factor, we get x minus 3 times x minus 3, which means that 3 is a double root. In other words, it has a multiplicity of 2, so it actually counts as 2 solutions. Now let's look at this graph. Okay, this is a cubic equation, but we only see one x-intercept. Well, when we factor, we get x times x squared plus 4. We have a real zero, x, but then when we solve x squared plus 4 equals 0, we end up with 2 imaginary zeros, 2i and negative 2i, and these do not appear as intercepts. So you're not going to see the imaginary zeros on the graph. But when you add the multiplicities together and you add in the imaginary zeros, you will get the same number of zeros as the highest power. Now this is pretty simple. All you have to do is tell me how many zeros the function will have. You don't have to tell me what they are, just how many. Pause the recording, try these, and then resume to check your answer. All right, you should have gotten 3 because it's an x cubed. That's the highest power. And for this one, you should have gotten 2 because it's x plus 5 squared. Now, the possible rational zeros can be narrowed down to a list created by taking factors of the constant term and placing them over factors of the leading coefficient. This is something we did last year. I called it making the list. So what you're going to do is you're going to create a list of possible rational zeros. If you don't have this list, then the zeros could be anything in the world. But this list narrows it down considerably from having an infinite number of choices for rational zeros to a much, much smaller number of choices. Okay, so for this polynomial, what you're going to do is you're going to take the factors of 8, which is the last term, don't worry about the minus, and you're going to take the factors of 3. So for 8, we have 1, 2, 4, and 8. For 3, we have 1 and 3. What we're going to do is we're going to place each factor of 8 over each factor of 3. So we're going to have 1 over 1, 2 over 1, 4 over 1, 8 over 1. And now do the same with 3 as the denominator. 1 over 3, 2 over 3, 4 over 3, and 8 over 3. Notice we put a plus or minus in front of each one because it could be the positive or the negative. All rational zeros will come from this list. However, not every number on the list will be a 0. In fact, it could be that none of them may actually be a 0. Now, back before graphing calculators, what you used to have to do was you would pick a number from the list and use synthetic division to see if it was a 0. If it was a 0, then we would factor this result of the division if we could, or if that wasn't possible, we would choose another number and divide again until we could narrow it down to a polynomial small enough to factor or use the quadratic formula. If it wasn't a 0, well, you crossed that choice off the list and tried again. And you did this repeatedly until you found all the zeros that could be found. Now today we have a graphing calculator we can use. So what we're going to do is we're going to look at the graph and we're going to determine which zeros on our list are likely to be zeros and then use synthetic division to confirm. Or we can use the calc 0 to find the solution. One final note is that both imaginary and irrational zeros will come in conjugate pairs, which means if 3 plus 4i is a 0, then 3 minus 4i must also be a 0, and this will be true with square roots. So if it was 2 plus the square root of 5 is a 0, then you know 2 minus the square root of 5 must. So here's an example to try. Find all the real solutions of the polynomial equation. Start by making your list of possible rational solutions. Then use your graph to determine the real solutions. Pause the recording, give it a try, and resume to check your answer. Okay, our possible zeros are 1, 2, 3, and 6, the positive and negative of all four of those. We get that from taking the factors of 6 and putting them over the factors of 1. When we graph, we can see that negative 2 and 1 would appear to be the real zeros of this polynomial equation, meaning that the two remaining zeros would be imaginary. This time you're going to use your calculator. You're going to use the zero or root function to approximate the zeros to 3 decimal places. So graph this function, then go second, trace, and use the zero application. You're going to find the zeros for each zero that you see there. Pause the recording, give this a try, and resume to check your answer. And you should have found zeros at negative 1.414, negative 1, positive 1, and 1.414. And just a side comment, you wouldn't have known this, but the negative and positive 1.414, that's the same as plus or minus the square root of 2. Okay, find a polynomial function with real coefficients that have the given zeros. There are many correct answers to this. Now, we've done this before. This time we're throwing in an imaginary zero. So remember what we said about conjugate pairs. Pause the recording, try this problem, and resume to check your answer. So what we're going to do is we're going to set up 3 parentheses, each with an x minus, and we're going to put in 1 and 5i, but then we're also going to put in minus 5i. And then x minus negative 5i will give us x plus 5i. So you have to have, it's got to have a minus and a plus for those imaginary roots. Then what we did was we multiplied the conjugate pairs together. X minus 5i times x plus 5i gives us x squared plus 25, and then finally multiply it out to get the answer you see there. A side note is that we can multiply this entire equation through by a constant and have an answer that will also be correct. Hey, same thing, except you got a few more factors this time. So pause the recording, give this a try, and resume to check your answer. Okay, so we know if 3 plus 2i is a 0, then 3 minus 2i must also be. You may be wondering, why are they doing 3x minus 2? Well, if you think about it, x minus something had to give us 2/3. If you set 3x minus 2 equal to 0 and solve, you get 2/3. So the bottom number, it's kind of like using the slide rule. The bottom number goes in front of the x, and the 2 will just stay where it is. Then we have x plus 1, we have x minus 3 plus the square root of 2i, and x plus minus 3 minus the square root of 2i. What I will probably do on this is actually let you leave those answers in that form, so you don't need to multiply them out all the time. Okay, if you did multiply it out, check through and check your work and see how you did. This time they're telling us 2i is a 0, and they want us to find all the rest of the zeros. You're going to use synthetic division to do this. It's the easier way to do it. 2i, you're going to divide that out first. Now, it's going to be a little messy. But remember, if 2i is a 0, negative 2i must be also. And when you divide that out, it gets a lot neater. Find all the zeros. Pause the recording, give this a try, and resume to check your answer. So dividing by 2i gives us, like I said, it's a little bit messy. You've got 1, 2i minus 1, negative 2i. But then when we divide by negative 2i, it gets rid of all the i's. So we end up with 1, negative 1, which is basically the end. So we have x minus 2i times x plus 2i times x minus 1. Alternatively, what you can do is you can say, all right, well, I know two factors are x plus 2i and x minus 2i. If I multiply those together, I get x squared plus 4. So x squared plus 4 must be a factor. And then you can use long division with the x squared plus 4, and you end up with the same answer, x minus 1. All right, try this one. Same idea. This one's going to be a little bit messier because you've not just got an I, you've got a square root. So be very careful. And remember, if negative 3 plus I square root of 2 is a 0, so is negative 3 minus I square root of 2. Pause the recording, give this a try, and resume to check your answer. Okay, so a little bit messy here. Now, you can do synthetic division with this. They chose to use long division. So what they did was they multiplied the two factors together of x minus negative 3 plus 2i and x minus negative 3 minus 2i, square root of 2i, excuse me. You multiply them together, you get x squared plus 6x plus 11, and then divide it into the larger polynomial. That gives you x squared minus 3x plus 2. Which can be factored into x minus 1 times x minus 2. And then that gives you the remainder of the zeros, which would be 1 and 2. Okay, write a polynomial as a product of linear factors and list all the zeros. In other words, factor it out and list the zeros. Pause the recording, give it a try, and resume to check your answer. Okay, this one won't factor, so you have to use the quadratic formula and simplify it as much as you can. And when you use the quadratic formula, you get 1 plus or minus I, which means our factors are z minus 1 plus I and z minus 1 minus I. So you see them there. And, of course, we know the zeros are 1 plus or minus I. Okay, now you're going to write the polynomial function as a product of linear factors and list all the zeros. So we're doing the same thing. I suggest you make a list of possible solutions, that you check your graph to see if one of those looks good, and use synthetic division. Pause the recording, give this a try, and resume to check your answer. So they listed the possible rational zeros, which would be factors of 6 over factors of 5. Checking the graph, negative 1/5 must have looked pretty good, so they tried that, and it worked. And we ended up with 5x squared minus 10x plus 30. You can factor a 5 out of that, and you get x squared minus 2x plus 6, which you have to use the quadratic formula on. And so the zeros are negative 1/5 and 1 plus or minus the square root of 5i. So we have x minus negative 1/5 times 5, because remember we factored the 5 out, so that's got to be in the final answer, times x minus 1 plus the square root of 5i, times x minus 1 minus the square root of 5i. If you multiply that 5 through the first parenthesis, it makes it a little nicer. You've got 5x plus 1, and then you've got the other two parentheses. All right, here's another problem. This is a quadratic type, so you actually can factor this. Just think of it as being x squared plus 10x plus 9, but don't forget it's not. Pause the recording, give it a try, and resume to check your answer. So we'll factor. Instead of x plus 1 times x plus 9, it's going to be x squared plus 1 times x squared plus 9. And then you need to factor those. Well, you can really solve them. X squared plus 1 equals 0, so x is plus or minus I. X squared plus 9 equals 0, which means x is plus or minus 3i. And then you can put those into the factors. X plus I, x minus I, x plus 3i, x minus 3i.